In today's digital world, it really feels like we're just constantly wading through this flood of information.
It's a lot, yeah.
New tech, new platforms popping up daily.
Yeah.
It's honestly easy to feel like you're just struggling to keep your head above water.
Totally. Information overload is real.
But what if there were these fundamental ideas, kind of like bedrock concepts, that once you really get them, everything else just sort of clicks?
The aha moments. Yeah, those are key.
That's exactly what we try to do here on the deep dive. And today we're diving into one of those foundational pieces, Kubernetes, or, K8s as everyone calls it.
K-ACE, right. The big one.
It's that open source powerhouse, the thing that automates deploying, scaling, managing all those containerized applications.
It's kind of the invisible engine behind so much of what we use online.
Exactly. So our mission today, for you listening, is to really demystify Kubernetes. We want to unpack its core architecture.
Get under the hood a bit.
Yeah, we'll focus on the cluster, the nodes, and that central command center, the control plane.
By the end, the goal isn't just knowing the definitions.
No, it's about understanding how K8s works its magic, how it keeps modern apps running smoothly, reliably, efficiently. It's that intelligent automation we want to explore.
Right. And that's the promise here. This isn't just reading a textbook. We want to spark those aha moments.
Make the abstract feel concrete. Yeah.
Exactly. So you walk away with a solid foundation, feeling, less intimidated by these complex distributed systems.
Okay, let's start big picture then. We hear Kubernetes, containers, distributed apps, but where does this stuff actually live? It all starts with a Kubernetes cluster, right?
Precisely. Think of a Kubernetes cluster like a powerful unified system. It's not just one computer.
No, it's many working together.
Exactly. It's a set of machines, we call them nodes, all networked and collaborating. Their whole job is running and managing your containerized applications.
And Kubernetes is the maestro conducting this orchestra.
The maestro, yeah. Making sure everything performs exactly as you told it to.
So this cluster, this interconnected system, what are the main parts we really need to get our heads around? The core anatomy, so to speak.
Okay, so at its heart, a cluster really breaks down into two main categories of components. You've got the nodes. Those are the machines actually doing the work.
The workers.
Yep. And then you have the control plane. That's the intelligence, the part orchestrating everything.
Or the brain.
The brain. And running inside all of this are your pods, which hold your actual applications.
Now let's pause here. For someone listening, maybe they're new to this, or maybe they use K8s but haven't dug into the why.
Mm-hmm.
Why is understanding this architecture so important? What's the real payoff?
Well, the real magic of Kubernetes isn't just that it runs your apps. It's how it's designed for things like scalability and resilience, how it handles failure.
You mean it fixes things automatically?
Often, yes. It's built to anticipate and recover. Understanding the architecture shows you how it achieves that incredible fault tolerance and automation. It's how it handles the complexity of managing, potentially thousands of servers.
So it hides the complexity.
Exactly. It lets developers focus on code, not infrastructure headaches. That's the real aha for a lot of people. It's not just running things, it's intelligently managing the chaos.
That's a great way to put it. Okay, before we go deeper into cluster parts, we've mentioned containers and pods a few times. Crucial terms. Let's nail those down first.
Good idea. They're fundamental. So containers, think of them like standardized shipping containers, but for software.
Okay, like a standardized box.
Exactly. A lightweight, self-contained package. It bundles your application code with everything it needs, libraries, tools, settings, the runtime, everything.
So it runs the same everywhere.
That's the goal. Consistency no matter where you deploy it.
Okay, containers the package. But then you said pods. Is a pod just one container?
Excellent question. No, and this is a key Kubernetes concept. A pod is the smallest deployable unit.
Smallest unit you actually manage in K8s.
Right. And a pod holds one or more containers. Crucially, these containers inside a single pod are always scheduled together on the same node.
Always together. Why?
They share resources, like networking and storage. Think of them as a tightly coupled team. Sometimes related processes need to communicate very closely, almost like they're on the same machine. The pod provides that shared context.
Got it. So a pod is like a little group of containers that need to stick together. Makes sense.
Okay.
What else helps us use these? You mentioned other concepts.
Right. So you don't usually manage individual pods directly. You use things like deployments.
Deployments. Okay, what's that?
A deployment is like your blueprint.
Yeah.
It tells Kubernetes how you want your application to run. You define, say, I need 3 identical copies of my web server pod running.
So it manages the desired state, how many pods you want.
Exactly. It handles creating them, updating them, scaling them, and then to let these pods talk to each other or let users talk to them, we use services.
Services for communication.
Yeah. Think of a service like a stable address or phone number for your application pods. Pods can come and go, get replaced, move nodes, but the service address stays the same.
So it provides a reliable entry point.
Precisely. It handles routing traffic to the right, healthy pods.
Okay, this is building nicely. We have the cluster, we have pods running our containerized apps.
Yeah.
But who actually runs these pods? The
Yeah.
heavy lifting. That's the nodes, you said.
That's exactly right. The nodes are the worker machines in your cluster. They are the actual servers, could be physical machines in your data center, could be virtual machines in the cloud.
The compute resources.
Yep, they provide the CPU, the memory, the storage where your pods actually execute. Every node runs a bunch of these pods.
Yeah, and you mentioned 2 types, worker and master.
Primarily, yes. We'll talk about master nodes when we get to the control plane, but let's focus on the worker nodes first. These are the ones dedicated to running your actual application workloads. They do the grunt work.
So what's actually on these worker nodes that lets them do their job? They're not just blank VMs, right? How do they connect back to the main brain?
Great question. No, they're not blank. Each worker node has several key components running on it. First and foremost is the kubelet.
Kubelet, okay.
Think of the kubelet as the node's agent. It's the piece of software that talks constantly to the control plane. Its job is to make sure the containers described in the pods assigned to its node are actually running and healthy.
Like the local supervisor.
Exactly. And the kubelet manages these containers using a container runtime.
Ah, so that's where Docker or Containered comes in.
Precisely. The container runtime is the low-level software that actually pulls the container images, starts the containers, stops them, manages their life cycle.
Got it. Kubelet talks to control plane, uses runtime to manage containers. What else?
Then you have kube proxy. This runs on every single node too. Kube proxy is all about networking.
Handling the traffic.
Yeah. It maintains network rules on the node. These rules allow network communication to your pods from inside or outside the cluster. It understands Kubernetes services and directs traffic accordingly, doing basic load balancing.
The local traffic cop.
Good analogy. And finally, of course, the pods themselves. The groups of containers running your applications scheduled onto this worker node by the control plane.
Okay, so each node is pretty busy. What's the bigger impact of all this? Why are these nodes so vital? And, the scary question, what happens if a node just fails? Hardware dies, network connection drops.
Well, the nodes are the cluster's capacity. They provide all the compute, memory, storage resources your applications need. The beauty of Kubernetes lies in how the control plane distributes pods across these nodes.
Spreading the load.
Spreading the load, optimizing resources, and, crucially, providing fault tolerance. And that answers your scary question. If a node does fail, power loss, hardware failure, whatever Kubernetes is designed for this,
Doesn't just panic.
nope. The control plane detects that the node is unhealthy or gone. And then, almost immediately, it starts rescheduling the pods that were running on that failed node onto other healthy nodes in the cluster.
Wow, automatically.
Automatically. This is its built-in self-healing capability. Your application ideally stays available, maybe with a very brief interruption for some pods, but often without any manual intervention needed. It just recovers.
Okay, that self-healing is huge. So if the nodes are the workers, the muscle, then the control plane has to be the brain, the orchestrator making it all happen. This sounds like where the real intelligence lies.
You nailed it. The control plane is the brain of the Kubernetes cluster. It's not just one thing, though. It's a collection of processes that constantly monitor and manage the cluster's state.
Making sure reality matches the desired configuration.
Exactly. It schedules the workloads, makes decisions, and ensures your applications run the way you specified. And usually, in production setups, these control plane components run on dedicated master nodes.
Separate from the worker nodes. For reliability.
Precisely. To isolate the management functions and make the whole system more robust. If a worker node fails, the brain keeps working.
Makes sense. So what are the actual components, the departments within this brain?
Okay, there are a few key players we need to know. First up, the API server. Component name, Kubernetes.
The front door.
Absolutely. This is the central hub. All communication, whether it's you talking to the cluster with kubectl or internal components talking to each other, goes to the API server. It exposes the Kubernetes API.
The communication backbone. Got it. What's next?
Next is etc. This is super critical. Think of etc. as the cluster's database, but more specifically, it's consistent and highly available key value store.
Key value store. So it stores the configuration.
It stores the entire state of the cluster,
Hmm.
all the configuration data, what nodes exist, what pods should be running, deployments, services, everything. It's the single source of truth.
The official record. Okay. API server for communication, etc. for state storage. Who does the scheduling?
Ah, that would be the scheduler. Component name. Kube scheduler. Its job is pretty straightforward conceptually.
Figures out where pods go.
Exactly. When a new pod needs to be created, the scheduler looks at the available worker nodes, considers the pod's resource requirements, CPU, memory, any policies you've set, node affinities, taints, colorations.
Lots of factors.
Yeah, it does a complex calculation to find the best fit, the most suitable node for that pod to run on, and then assigns it.
Optimizing placement.
Okay.
What else is in the control plane?
Then you have the controller manager, or Cube controller manager. This is actually a process that runs several different controller loops.
Multiple controllers in one.
Yeah. Think of things like the node controller, replication controller, which ensures the right number of pods for a deployment exist, endpoint controller, and so on. Each controller watches the cluster state through the API server.
Compares it to the desired state in etc.
Right. And if the actual state doesn't match the desired state, the controller takes action to correct it. A node goes down, the node controller notices. If too few pods are running for a deployment, the replication controller starts more. It's the reconciliation engine.
Constantly ensuring reality matches the plan. Very cool. Was there one more?
Yes, often there's the cloud controller manager. This one's a bit special because it's specific to running Kubernetes on a cloud provider like AWS, Azure, or Google Cloud.
So it talks to the cloud platform.
Exactly. It embeds cloud-specific control logic. It allows Kubernetes to interact with the cloud provider's APIs to manage resources like cloud load balancers, storage volumes, network routes, things that are specific to that cloud environment.
Gotcha. So it bridges Kubernetes and the underlying cloud infrastructure.
You got it.
Okay, that paints a clear picture of the parts. But let's connect the dots. How does this all work together? Say, I, as a user, want to deploy a brand new app. Walk me through that flow.
Sure, it's a really elegant dance. So you, the user, typically use a tool like kubectl. You write a definition file, maybe a YAML file describing your deployment.
Telling it what image to use, how many copies.
Right. You send that definition, that intent, to the API server.
Using kubectl apply-f my-app.yaml or something.
Exactly. The API server receives this, validates it, and then writes your desired state into etc.
Yep.
User wants this deployment with 3 pods.
Okay, the desired state is now recorded.
Now the scheduler sees via the API server that there are new pods defined in etc. that haven't been assigned to any node yet.
They need a home.
They need a home. So the scheduler does its thing, finds suitable worker nodes for these pods based on resources and rules, and updates the pod definitions in etc. with the assigned node name.
Okay, now etc. knows where they should run.
Right. Now the controller manager, specifically the relevant controller like the deployment controller, sees the overall state. It might see desired, 3 pods, actual, 0 pods running. It knows action is needed.
Time to make it happen.
Exactly. And the kubelet on the chosen worker node is constantly watching the API server for pods assigned to it. When it sees a new pod assigned, it talks to the container runtime.
Tells Docker or container to start it up.
Pull the image, create the container, start the application defined in the pod spec. Then the kubelet reports the status back to the API server, pod is running, pod failed, etc.
Which updates etc. again.
Which updates, etc. And this whole loop, desired state, etc., controllers observing, schedulers placing, kubelets acting, status reported back, it runs continuously. It's a constant reconciliation loop ensuring the cluster matches your intent.
That workflow really shows the intelligence. It's not just one command. It's this ongoing process. This whole system, the brain and workers together, sounds incredibly resilient. What are the really tangible benefits of this architecture? How does it pay off day to day?
The payoff is huge. The synergy between the control plane and the nodes delivers Kubernetes' core promises. First, high availability.
We touched on that. The control plane itself is redundant.
Right. In production, you run multiple master nodes, etc., is replicated across them. So if one master fails, another takes over. The brain keeps working. No single point of failure for cluster management.
Critical for production. What else?
Scalability. The control plane constantly balances pods across your worker nodes. If you need more capacity for your app, you can tell the deployment, I need 10 pods now instead of 3.
And the controller manager makes it happen.
The controller manager sees the change, the scheduler finds nodes for the new pods, kubelets start them, it scales up. And it can scale down just as easily when demand drops, saving resources.
Smart. And adapts to load.
Then there's the self-healing we talked about. It's worth emphasizing again. Pod crashes. Controller manager restarts it. Node fails. Scheduler replaces its pods elsewhere. It automatically recovers from common failures.
That saves so much operational headache.
Immense amounts. And finally, updates and rollbacks. Deploying new code used to be stressful.
Downtime windows. Careful planning.
Exactly. Kubernetes manages rolling updates. You tell the deployment, use this new image version. It gradually replaces old pods with new ones, ensuring the app stays available throughout if the new version has problems.
Rollback.
One command to roll back to the previous, stable version. Again, minimal or no downtime. It provides a safety net for deployments.
It really is a framework designed to take the complexity out of managing modern apps, hiding it behind this layer of automation, making the infrastructure feel, well, almost invisible when it works well.
That's the goal, yeah. Abstracting the infrastructure complexity.
So we've really covered a lot of ground today. We've taken that deep dive into Kubernetes, unpacking how the cluster, the nodes, and the control plane all interact.
The big picture and the key components.
Yeah. And hopefully you, the listener, now have that solid grasp. Nodes are the workers doing the job, running your apps. The control plane is the smart manager, the brain, orchestrating everything to match your desired state.
And the core message really is that Kubernetes automates tasks that used to be incredibly difficult and prone to error. It's just a very robust, elegant way to manage containerized applications at scale,
Simplifying these complex distributed systems.
making them manageable, resilient, and scalable. So maybe here's a final thought for you to chew on. We've seen how Kubernetes excels at automating deployment, scaling, and self-healing, reacting to the current state.
Right. It fixes things after they happen or scales based on current load.
Exactly. So thinking ahead, how might this kind of self-managing system evolve? Could it move beyond just reacting to actually predicting potential issues, resource shortages, impending failures, and maybe even preventing them before they occur?
Proactive instead of reactive.
Yeah. What would truly invisible, predictive infrastructure look like? And maybe more importantly for you, what new kinds of applications, what new frontiers in development might that kind of future unlock for your own ideas and projects?